Pour ceux qui sont en Zoom, pardon. Hugo. So I'm going to speak English now. I am connecting my computer to my own personal, my laptop to the video. I don't think that's what normally is the case. I'm just going to see if there's another way of doing it. Is there anyone from the M2K? Yes. Okay. Does anyone, like, do they normally do the Zoom calls with that video working? Or? Yeah, it's working. Okay, but it's because I'm using my laptop, I think. Because the sound is very beautiful. Yeah, that's why I think it's Hello. Bettina Couvière, c'est la meilleure conversion. On va l'avoir demain matin. C'est maintenant que Là, tu vas pas c'est pas tu veux pas voilà. Ah, voilà. Vas-y, fais coucou. Non, c'est là. Les droits, les droits. C'est parce que c'est la limite. Moi, il y a les gars, c'est dans le niveau de moi. Ils vont voir un petit peu les mots. On va l'enregistrer sur la chaîne. Ah, oui, d'accord. On va écouter. Je vais pas parler pour faire. D'accord, mais. Non, on va pas je ne veux pas faire un montage. Tu veux pas comment tu fais tu peux pas la faire assez Right, so can I double check that you can all hear me on the Zoom? If I change the loudspeaker and camera system, can you hear me? Okay, good. Right, so hello, everybody. I've met the M1 students before, who came to the previous courses. So, but very briefly, we did one session together in the first semester, but then there were the online courses. And so just for the M2 students to explain that the Masters 1 students had an initiation to statistics in the first semester. And so they have seen some of the course, but since this second part of the course is in English, and since the way it was taught in the first semester was mainly taught in a very kind of applied way, there will be, so just for the Masters 1 students, there will be some parts of the course which are almost identical to bits of what we did previously, but then for you, it's a way of revising, and also I'm speaking English. So that way that make you maybe more comfortable for those of you who are less comfortable in English. And also, there will be some initial course parts of the course which are going back to some of the basics, because in the first semester it was very quick outline of what we wanted you to know, and now we'll be going a little deeper. For the Masters 2 students, I am treating this as a first course in statistics, so you don't need to worry about maybe not having done what they did. Can I just ask the M2 students where you come from and what courses you did previously, especially if you have done any statistics? So maybe those who are present first.
Yes, so we are in M2 care.
Yeah.
So we didn't have any course during the master, but during the license we were in biomip. So it's biology with mathematics, informatics, and physics.
So you did some maths and statistics in that course. The three of you? All you?
So I was in bachelor, but I was not in the math course. I did not I just did the bachelor, the normal PCP bachelor, so we did have some math, but
not much. So what's PCP? Physics?
No.
During the first
Biology.
Physiology.
Right. For the others who are on Zoom, have you written something down, or otherwise you can speak up? Okay.
On Zoom, all of us, we are from M2 Care.
Yes, okay. So can you tell me if you have done any statistics beforehand?
So actually, me and Antoine, we are joining M2 Care, but we are into the equivalent of MD PhD programs. So we are dentistry students and we are taking a gap year to do our master too. But so we had in our past courses with you about statistics. But
Okay,
the other, I
So
assume the same.
Okay, so Antoine Magna, and you did PASS, is that right?
Yes.
That's what you're saying? Yes, okay. And the other students?
Can you hear me?
Yes?
Yes, so most of the people from care are coming from like not France, and also they have very different backgrounds. So except few people from care came from the BCP, I think like Luna, Sophie, Hélène, and I. And so we did a bit of statistics, but not much.
Okay, right. Well, in any case, so what this means is that everyone comes from different backgrounds, apart from, so the M1 students, you also come from different backgrounds, but you have already had an introductory course. So what this means is that I have to cater for people from very different backgrounds. So for some of you, maybe sometimes you'll be thinking, oh, this is a bit slow, I know this. And then other times, maybe it'll go a bit further. You obviously give me feedback on on the lectures, that's not a problem, but you have to realize that we're catering for different backgrounds and abilities. And the idea is that at the end of the semester, you will all have a basic baggage in statistics. So I'm just going to give you the outline of the course. So yeah, so the other thing is on Moodle, there is the M1 Moodle, and there's a link to the M2 space. So I think I will put everything on the M2 space just because it's easier to not, I think there's one or two things on the M1, but mostly on the M2. So make sure you go and check there. If there was any change in time or whatever, then I'll write it down there. And what I will do is I will put up the slides for the lectures. I'll try and put them a week before or a little before we start. So if you went and had a look before today, you might have seen the whole lot, but I decided to restrict it to just as we go, because I'd really like you all to come to the lectures, okay? Last year, I had to put everything online because I actually wasn't there. I was at the other end of the world, but this year I'm here, so it's nicer if we can be there. Obviously, I know there are some M2 students who are doing a placement in other countries or elsewhere. That's why we do have a Zoom session for them. So the course outline, the course I called Applied Biostatistics. Statistics is a very broad subject, and there's a lot that you can do, and pretty much every chapter you could talk about for 20 hours if you wanted to, which is not what we're going to do. You don't have necessarily backgrounds in mathematics or statistics. I will be showing formulas because I think that if we don't look at the formula at some point, it's going to be a bit of a black box for you, okay? The stats, you're going to be just, okay, I'm going to click on that and this is going to happen. So the aim is to explain a bit of how things work and what's inside the black box, but I won't be expecting you to write formulas or learn them off by heart, okay? So that's the first thing.
Excuse me?
Yes?
Yes, so we can see the camera, but we cannot see the
Sorry,
screen.
I haven't shared. Yes, sorry, I haven't shared the screen. Is that working?
Yep, thanks.
Okay, good. Yeah, and another thing, how good is your English comprehension? Is it okay when I speak like that? Can you understand me? Yeah? So if you have a doubt about something, I will very gladly re-explain in French, okay? I'm here for you to understand the stats, but since some people are not English speakers, French speakers, and for your general benefit, it's good for you to have lectures in English. We're doing it in English, but if there's something you don't understand, I can repeat it in French. I don't know any other languages, I'm sorry. Well, I know a little, but not enough to do a lecture in them. But okay, if there's a language problem, and also if you would prefer the French versions of some of these lectures, I can give them to you, the slides, okay? And in the exam, you can write in whatever language you like. Well, no, sorry. In the exam, you can write in French or English, not whatever language you like, because I'm sure you can speak other languages. But French and English will do, okay? Right. So, yeah, so I was saying the, now is this going to work? Yeah, so the prerequisites, what I am going to consider that you know a bit about is basic descriptive statistics. What's a mean, what's a median, a variance, standard deviation, etc. We will mention them again, but I'm assuming you know what those are. And a few things about distributions, although I've decided that actually I'm going to give you, so actually the second line is not true because today we're going to talk a bit about the main distributions that you need to know about. And the aims of the course are to enable you to acquire the statistical knowledge required to design a study, an experimental observational study. So when I have a problem, when I'm faced with some data and I would like to analyze it, am I capable of writing a statistical analysis plan, identifying the hypotheses, identifying the tests I'm going to use, and especially know how to analyze and interpret the results of a statistical study in parametric and non-parametric tests, including some modeling. So when I say analyze and interpret, it means can I actually, do the study, the statistics, and then interpret the results. Those are the main points I wanted us to examine during this course. So this doesn't work on that screen. It's not much use. So today we'll probably cover chapter 1 and some of chapter 2. So talk about main continuous distributions and their uses, point estimates and confidence intervals. Then we'll have a chapter where we're talking about the general principles of hypothesis testing. So for this, you will have seen some of that in the first semester for the M1 students. How to verify whether a distribution is normal. Chapter 5, main parametric statistical tests, some modeling, some analysis of variance, and some non-parametric statistical tests. And I don't think we will have time for chapter 9, but maybe that's possible. Okay, are there any questions about that? No? So I put that up on the screen. Okay, not quite sure how that's working, but let's change something. Okay, so first course, first chapter. Right, can everyone see that, including those on Zoom?
Yes.
Thank you. Right, on Zoom, if you have questions, you can write them in the chat, but I probably won't look at it very often, so don't hesitate to start talking, or when I say, does anyone have any questions? It's easier if you actually speak, because I might not notice if you write a question in the chat. Okay. So, we're going to talk about the main continuous distributions and their uses. We're going to go back on what the different types of random variables are, the definition of a probability density function and a distribution function, and give a few examples of continuous distributions. Now, as I said, I'm aware that everyone hasn't done mathematics, though some have. But the idea is just to give you enough background so that when we talk about some things in the next slide, you know where it comes from. So that's the idea. So the very important point in statistics is to remember that we are usually trying to find out some information concerning a population. A population in statistics means a large and possibly infinite collection of units, which can be individuals. So I wrote people, but obviously it can be mice, it can be regions, it can be anything on which we are measuring a characteristic, and we want to get information about these characteristics. Unfortunately, by definition, I can't use my pointer. So by definition, we cannot have access to all the information concerning the population. So we have to take a random sample of the population. The sample is a subset of the population, and in the sample, all the each unit is observed, and we are able to measure the characteristic we're interested in on each of these units. And so we can calculate we can calculate observed parameters on this sample, which are, the formula are chosen such as they are estimations of the unknown parameter, corresponding unknown parameters in the population. And so then the idea is to use statistical testing to make inferences about these unknown. The whole point in statistics is that you've got to remember that when you're doing a study, when you have mice, for those of you who are doing experimental pharmacology, or when you're doing biology, you have a set of patients, you have a set of mice, you have characteristics of this set of people. They are always only representative of a larger population, because you have no interest in saying this has happened for my 10 mice, or this has happened for my 20 patients. The whole point is you want to say something about the population from which these mice or people or units are drawn, okay? And so the whole strength of statistics, and the whole point and the reason why statistical inferential statistics were developed is that they enable us to, based on a sample, make inferences, draw conclusions about the population, okay? And so to distinguish between what is related to the population and what is related to the sample, we use Greek letters for the population, mu, sigma, and Latin letters for the sample. So this is just it's just notation. You could use anything you like. It's a way of distinguishing between the two. So descriptive statistics are what we use to summarize the data at the sample level, and inferential statistics. So inference, do you know what that means? That means to draw conclusions about something. Inferential statistics allow to extrapolate results observed on a sample to the populations from which they are derived. And the population has to be described by a probabilistic model, because we have to assume that when we take the sample is representative of the population. And so we have to have a model, a probabilistic model of the population. And so inferences mean finding the characteristics of the probabilistic model based on the available sample. And so when you have a question, so when you're doing an experiment and you want to know whether this drug has this effect or whatever, this bacteria does this to your sample, the questions you are asking, you have to remember that you're not asking them on your sample, you're asking the questions on your population. So your hypotheses are always made on the population, but you are going to set up the experiment and calculate statistics and tests on the sample to answer the questions in the populations. So to do all that, we need to remember that there are different types of variables. And this is a very basic slide, but I can tell you that when people come and see me, students write to me, or colleagues who are not in statistics and say, I've got this problem, I'm trying to do this. Often they're not necessarily aware of different types of variables. And why is this important? Because depending on the types of variables we have, we use different tests. So you've got to be very good at knowing which type of variable you have, because then you will use different types of tests. So variables can be either quantitative or qualitative. Quantitative, what does that mean? Can you tell me, so you ignore this column for the moment, what is a quantitative variable as opposed to a qualitative variable? And the same, if you want to answer me I've just realized I've gone away from the camera. Sorry for everyone who has something. So yeah, can you tell me what's the difference between a quantitative and a qualitative variable? You can answer in French if you prefer. Yeah.
Quantitative is with numbers.
Mm-hmm.
Well, qualitative, it's not a variable, like it's yes, no, or.
Yeah, that's good. Yeah, that's good.
Qualitatif, c'est une proportion, un rapport.
Alors, no, not necessarily, because if you have a proportion, then you still have a number. You see what I mean? But you may describe the distribution of a qualitative variable in the population using a proportion, but the variable itself is not if you have a number, then that means you are quantifying something. But you're right. I think you're getting at something which is true, but you've got to be careful how you say it. So let's give some examples. That'll be easier. So what an example, so quantitative, to go back to it, is a variable that is measured using a number, where the number has a meaning for that variable, okay? And we can have discrete or continuous variable. So what are examples of discrete quantitative variables? What are examples of continuous quantitative variables? Can you give a few examples? So discrete variables, for instance, the number of children in a family, the sum of the points on a dice. Continuous variables, that's probably the one you think of immediately, are height, weight, cholesterol rate, account. Okay, all those are continuous variables. So you can give a number for someone's height, and if I say 178 centimeters means something, you can measure it, you can reproduce it. So, and the difference between continuous and discrete means that it's not that not every value in the real number set is possible, okay? So you can't have 3.2 children, you have 1, 2, 3, etc. Okay? So that's discrete and continuous. Now, what about qualitative variables? There are 3 subtypes of qualitative variables: nominal, ordinal, and dichotomous. Maybe dichotomous is the easiest. Can you give me examples of dichotomous qualitative variables? Dichotomy means 2 possibilities.
2 examples, say yes, no.
Yes, no. Ill, healthy, open, closed, on, off, 0, okay? Those are dichotomous variables. Now, the difference between nominal and ordinal, nominal means something where you cannot classify the categories. So the color of the eyes, the blood group, AB, and O, you can't classify them. Whereas ordinal would be when, although you can't attribute them a number, you are able to classify them. So for instance, cancer stage, level of education, they do not correspond to numbers. So if I say there's a cancer stage 1, 2, 3, and 4, 1, 2, 3, and 4 are numbers, but why is it not a quantitative variable? Why do you think cancer stage level 1, 2, 3, and 4 are not quantitative, yeah?
Because it's not quantity of the group, it's just
because it doesn't correspond to anything. It's just a code, okay? It's a code. The same for level of education. Well, you might describe it, I have a bachelor, I have a master's degree, I have a PhD. You could say 1, 2, 3, but that's a codification, but there is an order, so you can say which level of education is higher than the other. Okay, so this, as I say, can seem very basic, but it's important because when you come to do analysis, you need to remember, you need to be able to say what type of variable you have in order to choose the correct statistical test. And so random variables can be of either type, quantitative or qualitative, discrete, continuous, etc. And a random variable is characterized by its distribution. So one thing which you said, which was true, is that, for instance, if you wanted to describe the distribution of blood group in a population, then you would use proportions to say there are 30% of group A. Is that what you meant?
Oui, enfin, je voulais dire que les résultats sont représentés en proportion.
Voilà.
Voilà, même on-off.
But the value of the variable, okay, is A or B or AB. The value of the blood group is A or B. Whereas when you're in a quantitative variable, the actual value of the variable is 3.8 or 123, you see? But when you describe the distribution, then you use proportion. So this is one of the areas where you get it wrong. Okay, students, when I give examples in an exam and I say that there's a table and it says 30% were group A, 40% were group B, people say, oh, well, there's a proportion, so it's a number. So it's a quantitative variable. Okay, be careful because the variable itself for the individual is not 30%. It's I'm group A, you're group B, etc. okay? So knowing the distribution of a random variable enables us to calculate its probability. So if the random variable is X, you'll be able to, if you know the distribution, you can calculate the probability that X is either equal to something, if it's a discrete variable, qualitative variable, or that X is between two values. So we are going to talk only about continuous variables for this chapter, because that's the type of variables that is probably hardest for you to apprehend. But we will be talking about other types of variables later in the course. So what is the probability density function of a continuous variable? A continuous variable, by definition, has an infinite number of possible values, okay? Because it's on the real line, it can have an infinite number of values. And so it's not possible to list the probability of observing each individual value. You can't say, what's the probability of being this value? So the probability distribution is a continuous function. And what we call the probability density function, sorry. What we call the probability density function of a continuous random variable is a function which is always positive. So f of x is greater or equal than 0. And the integral of this function is equal to 1. So don't worry, you won't be doing any integrals, but you need to realize that the area under the curve is equal to 1. That's very important in terms of probability, okay? So you need to remember that the function is always positive, and the total area under the curve is equal to 1, because we will use that later. So the probability that x, which is the random variable we're interested in, takes values between a and b is equal to the integral between a and b of the function, the probability density function. And so I want you just not to concentrate too much on the integral, because maybe you've never learned integrals, but that's okay. Just remember that when you do the graph of a function, the area under the curve is equal to the integral. And when we, I'll do it this way, then I use the, when you trace the function, the area under the curve between the values a and b corresponds to the probability that x is between a and b, okay? So that's an important thing to remember. So the distribution functions are defined by mathematical functions, and there are some natural distributions. There are some natural distributions which are useful to model phenomena observed in the natural world, such as Bernoulli binomial Poisson normal distribution. And then there are some non-natural distributions which are being created by mathematicians and used for technical reasons. And so why have they've been invented to be able to do certain statistical tests, calculate confidence intervals. And some examples of non-natural distributions are the chi-squared distribution, student distribution, Fisher distribution. So student and Fisher are names. And so in that list of distributions, the red ones are continuous distributions. We won't talk about Bernoulli binomial and Poisson distributions, but they are distributions which are apply to qualitative variables. We'll concentrate on the continuous ones. So just so that you realize that you can actually see normal distributions in the natural world, whereas you can't actually observe the others. They constructed distributions. So the normal distribution, or Laplace or Gauss distribution, is the most important distribution in statistics. Because it's very frequently used to describe biological variables. The reason for that is that it's a distribution which represents correctly any variable which results from a large number of independent phenomena. And a lot of things in our world are that. So your height is the product, how tall you are, is the product of lots of independent factors which make your height. And so that's the case for a lot of biological variables, which is why most biological variables are represented by this normal probability density function. It's a distribution which I'm sure you know about, you've already seen, this very famous bell-shaped distribution. And so the formula is not a very nice one, but I did write it down. F of x is equal to 1 over sigma, etc., where mu is the mean and sigma is the standard deviation. Sigma squared is the variance. And so, yes, the fact that this is called the law of large numbers, the fact that a large number of independent random variables of the same order of magnitude, when you sum them, the result is a new variable with a bell-shaped distribution, the normal distribution. And so that is a very strong, the law of large numbers and central limit theorem are very fundamental to a whole load of statistical theorems. So this property, the central limit theorem, allows calculations to be made without knowing the distribution of variables when there are large samples. So we'll talk about it a bit later. Now, a normal distribution, how do we describe a normal distribution? It's symmetrical about the mean. So you can see that, now, if I move this, I want to find a way to point to things so that everyone can see them. I see that. Okay. Now you can all see it. So you can see that all these are 4 different normal distributions. So what is the difference between the blue distribution and the green distribution? You can see that the blue distribution has a mean of 0 and the green one has a mean of -2. But in all these cases, in the 4 distributions, you can see that the distribution is symmetrical about the mean. Now, the blue, red, and yellow distribution have a mean of 0. And what can you say about the variance or the standard deviation? Which has the largest standard deviation? Which curve has the largest standard deviation or the largest variance? The yellow one, okay? So the flatter the curve, the larger we call it la dispersion, the dispersion of the variable. Okay, it's telling you that the variability is very large, and the narrower the curve, the smaller the standard deviation. And an important distribution. So there are lots of different normal distributions. They are defined by their mean and their variance. So here you see we gave, there's an example of 4 different normal distributions, 3 means of every time what characterizes the normal distribution is their mean and their variance. So you can see 4 different combinations. And a very important normal distribution is the standard normal distribution, which has a mean of 0 and a variance of 1. Why is it such an important distribution? Because you saw the formula for the probability density function of the normal distribution. So doing the integral of that big function is very difficult. So instead of doing that, we transform the variables to use the standard normal distribution. And so when we have any normal distribution with any mean, mu, and variance sigma squared. So if x is a random variable following a normal distribution with mean, mu, and standard variance sigma squared, you can transform it into a standard normal distribution by subtracting the mean and dividing by the standard deviation. And we call this new variable z. And this new variable follows a normal distribution with mean 0 and variance 1. So when we want to know the probabilities for a normal distribution function, we can easily use this transformation, subtract the mean, divide by the standard deviation to obtain un encadrement. I forget my English words as well. To obtain this formula where we are looking for the values of z. And so that means that whatever the normal distribution, the standard normal distribution is sufficient to calculate probabilities associated with it, okay? You can go from any normal distribution to the standard normal distribution to do calculations. So this is an example of the standard normal distribution table. So this table gives the values of Z such that alpha is equal to the probability that Z would be greater than that value. So this is the probability density function of the standard normal distribution. So there's a 0 in the middle. And what the table gives is probability that Z, that follows the standard normal distribution, is greater than Z alpha is alpha, okay? Alpha is the probability that Z is greater than Z alpha. And we said before, remember this one? We said that this is how you define a probability, is you look at the probability density function, and the probability is the area under the curve between two values, okay? So that's very important. So, if we look at this table, so in the table are the values of Z, so you can see they go from minus 2.6 to 2.6, so, and there's a 0 in the middle somewhere here, okay? And these are the values taken by the standard normal distribution. And on the sides here, we have the corresponding probability. So if you look at this, 1.15, the probability that Z, something that follows the standard normal distribution, is greater than 1.15 is equal to the sum of the corresponding line and the corresponding column. Okay, so that gives you 0.1 plus 0.025, so 0.125, and you can this is a probability, but you can transform it into a percentage, and it says that 12.5% in a standard normal distribution have a value greater than 1.15. So we're going to have an example. So now you're going to work. So you take a piece of paper and try and solve this problem. So let X be the birth weight in kilos of newborn babies, approximately distributed according to a normal distribution, with a mean of 3.3 kilos and a standard deviation of 0.5. So does that seem to make sense to you? A mean baby weight is 3.3. Depends how big or small you are. That's a bit small for my babies, but you know. But okay, makes sense. So what we want to know is what is the probability that a newborn should weigh 2.5 kilos or less? So if we write this on the board, now I need to learn how to turn this thing to the board. See if I can.
In any case, the green is reversed. So when we watch through the camera,
you can't read what it says.
Or you can get on the.
No, it's too complicated. Well, I can if I want to, but well, well, so I'll just do a quick representation of the normal distribution. We said that here it was centered on 3.3, okay, with a standard deviation of 0.5. Okay, and so what we want to know is the probability that the newborn should weigh 2.5 kilos or less. So if this is 2.5 kilos, where can I represent the probability that we should be less than 2.5 kilos? Where can you see it on the graph? Yeah, it's this area here. Area under the curve here. This is the probability that X is less than or equal than 2.5. So what would you say that probability is greater or less than 50%? Less than 50%, okay? So you should find something smaller than 50%. Now, what are you going to do? You're going to use, so I'm asking you not to cheat and look behind. You're going to use this table, and you're going to use this, so you're going to go from X to Z. So how do you go from X to Z? You have to subtract the mean and divide by the standard deviation, okay? And once you have this formula for Z, you can then use the table to find what you're looking for. Is that okay? So we can have a look at it and we will do it together in a minute. So I'll just write, I'll write the question again. Well, you have it on the board. It's what is the probability that X is less than 2.5? Okay. What is the probability that X is less than or equal to 2.5? You have to transform it. Sorry, I'm giving you a solution. You have to transform it to get it in the form of Z. And then you'll be able to look at the table to find the right value, okay? So have a little think about it. Alors, have you managed to transform the variable from X to Z? Yeah? Or not? So, what we need to do is first transform from X to Z. So it means we need to subtract the mean and divide by the standard deviation. So this becomes 2.5 minus 3.3 over 0.5 is minus 1.6. So this is a new variable Z. And we know, because of the formula we saw earlier, that this follows a standard normal distribution. So we are looking for P of Z less than or equal to minus. So what we're saying is that is equivalent to this with us. Higher up. This is equivalent to. So I'm making it smaller, but okay, it's equivalent to 0 minus 1.6, and that probability. B of Z less than or equal to minus 1.6. Now, if you look at this, what do we have? We have the probability that Z is greater than minus 1.6. So what can we do to find that when we have the table giving us that? The other side, greater than. Who has an idea? The table gives, yes?
La chiffre de alpha colonne, c'est combien chiffres après
Ici, vous voulez dire?
Oui, 1,5
Yeah.
80
That one, yes. Yes. So, but just the question is, so you're right, we are going to be looking at this number. What I want you to realize is that the table gives probability. If I look for this number, I can look for this number, minus 1.6, it's here. Then it is going to give me the probability that Z is greater than minus 1.6. So it's going to give me this area, okay? So we can look at it that way. What is the probability that Z is greater than minus 1.6? So I look here. So I look at the closest. So, okay, this is the closest. The probability is 0.045 plus 0.9, okay? So it's 0, it's this, okay? Yes? So how can I get this if I know that?
1 minus.
Exactly, we said the total area under the curve is 1, okay? So what we are looking for is 1 minus P of Z greater than minus 1.6. So we've just written it, so that means it's equal to 1 minus 0.945, which is 0.055, yes, thank you. Okay, and so that is something which is smaller than 0.5, which we said it should be. And so that means that if we put it in percentage, 5.5% of, so if we go back to the way I wrote it. So here, yeah, we find 0.055, so it means the probability that a newborn is less than or equal to 2.5 kilos is 5.5%, okay? And that makes kind of sense. Another way we could have done it is to say, because we know that the distribution is symmetrical, we could have said that this is equal to P of Z greater than what? How can we say that this 1.6, 1.6, okay? So we could have done that, said that it was equivalent to P of Z greater than 1.6, and if you look at 1.6 here, you get 0.055, okay? Because the distribution is symmetrical. Okay, you can, just for those who are on Zoom, so because, yeah, we know that the distribution is symmetric, so we can look at P of Z greater than 1.6, that's equivalent, and so we would have got the same answer. Right, second question. What is the probability that a newborn weighs between 2.5 and 3 kilos? So now that you know how to do it, I think you can work that out all by yourselves. Probability that a newborn is between 2.5 and 3 kilos. Okay? What is that equal to? Can have the table here, or you have it in front of you maybe. Find the probability that X is between 2.5 and 3 kilos.
Parce qu'avant, on avait zéro, je ne sais pas comment faire pour c'est pourquoi pourquoi c'est Z, c'est Z. Non, c'est ça. Moi, j'ai c'est ça. C'est ça, c'est ça, mais c'est pas aussi. C'est pas de je me
Alors, c'est bon, vous avez, sorry, have you found the right answer? Wait, I will wait.
C'est le 3, ça fait moins 6, là, c'est moins 0,3 divisé par 0,5, ça fait ouais, le poids que vous avez moins 0 génère.
Have you finished?
Yes.
Yes? Good. So, would someone like to tell me, would you like to tell me what you found? How you did it? You can say it in French if you want to. No, say it in French. It's all right. Go ahead.
0,22.
0.22. What did 0.22? Has anyone else found that value? Yes or no? Yes? Put your hands up. Okay, yes, that's right. Well done. Yes, good. So you see, the difference with what we did before is that you have two values, so you have to still transform it into Z by subtracting the mean and dividing by the standard deviation. And then because we have two sides, so if this is not, did anyone have any difficulty going from there to there? Do you know why this is equal to that? So this, if you have doubts about why it's true, that's why it's very helpful to look at a graph like this, okay? We're looking for the probability that X is between 2.5 and 3, so this area, okay? What color have I got there? Marine, okay, this area. And so when you think, okay, what is this area equal to? I can say, so because the table gives greater than, it's better to go this way, okay? So I can say that this area is equal to P of X greater than 2.5 minus P of X greater than 3, yeah? So that's how I go from there to there. Because you can look at the graph and see that this area is the same as that minus that. And we could say it's the same as that minus that, but then that's not what the table gives us, okay? Do you understand? Yes? Okay. Right, so then you go and look in the table for P of Z greater than minus 0.6, that 1.6, we found that before, it was 0.9745. And the other one is P of Z greater than minus 0.6, so that was there, and so that's 0.725. You do the sum of the two, the column and the line. And so, you get this difference, and that is 22. So this means that 22% of newborns weigh between 2.5 and 3 kilos, okay? Now, this is a very simple example, but the idea is to start getting you, to show you how we use distributions in real life, okay? So one of the very important properties you need to remember about the normal distribution is that for any random variable x which follows a normal distribution, and as we have said, that is a lot of the variables we know, approximately 68% of values of x are within one SD, one standard deviation of the mean, okay? And how do we know that? How do we know that 68% of values are within one SD of the mean? Because, listen to me, if this is any random variable x following a normal distribution with mean mu and standard deviation sigma. If we go from x to z, then we subtract mu, we divide by sigma. So we would be asking how many percent of values are within -1 and +1 of 0, yes? -1 and +1 of 0. So if we look in the table, what is P of z greater than 1? P of z greater than 1 is what? 0.15, maybe this one, or 0.16. And then greater than -1 is 0. Well, why don't you calculate? Calculate the proportion that is between -1 and 1 in the standard deviation, in the standard normal distribution. P of x, P of z between -1 and 1. Okay? Standard normal distribution. -1 and 1, and between -2 and 2. Find me P of z between -1 and 1, and P of z between -2 and 2. What are the values?
Ça fait 0,13 pour le premier.
Ça fait 0,13?
À premier calcul, oui. 0,85 moins 0,72.
Well, look at the graph. Look at the graph. Is it possible? You're saying that this, all this, is equal to? So we're asking about all this. You say it's 13%? Okay, so that's what you say. See if anyone finds anything different. P de Z entre -1 et 1, en regardant la table. 0.68, how did you find it?
Because minus 1 is 0.84.
Yeah, so the probability that Z is greater than -1,
0.984.
voilà, is 0.84, okay? So this is equal to 0.84 minus,
Minus 0.16.
and that is 0.68, that's better, 68%, okay? Now find P of Z between -2 and 2. So someone find the number that is closest to -1. So this or this, 60.16, and then this one is 0.84. Oui, entre -1 et 1. Donc là, vous avez, on fait d'abord. So first, you first look at P of Z greater than -1. So all this, that is equal to, did you find it? So it's about equal to P of Z greater than moins, which is, c'est quoi ça?
Moins 1,6.
Pourquoi moins 1,6?
Non, c'est 0,84.
No, this is the number. This is the,
C'est 0,84.
voilà. This is here. And you're looking for the probability. The probability is the sum of that plus that. Yes, so 0,84. C'est ça? Ouais. 0,84 moins 0,7. Et donc, ça fait bien 0,68. Vous êtes d'accord ou pas? C'est bon? Now, if you take this one, P of Z between -2 and 2, P of Z between -2 and 2, what do you find for this one?
C'est ça. Non, non. Donc, on a.
Does anyone count this one? -2 and 2? 0.95. Does everyone agree with that? Yes? Have you got the difference between the numbers and the probabilities? Yeah? Okay. Is everyone okay with that? So you said P of Z between -1 and 1 is 68%, and P of Z between -2 and 2 is 95%. And because that was true for Z, for any X, the 68% of the values are between -1 and +1 SD. Donc, on rajoute the standard deviation because that is any normal distribution, whereas the other one was just the standard normal distribution with a mean of 0 and a standard deviation of 1. Do you understand why that works? So this is true for any normal distribution. So that means that if I say to you, the height of the students in the University of Toulouse is 165. I don't know, I'm just saying it's 165 and with a standard deviation of 0.4, then you can tell me that 68% of students measure between 1.6 minus the standard deviation, and do you know what I mean? So that is how we construct, for instance, you know, in your carnet de santé, at the end, when you have the curves for how high and tall you are, they've been used based on the distributions in the French population. So that is a very important thing to remember. Now, if we go further, so that was a lot about this normal distribution because it's a very important distribution. Now we're going to talk about the chi-squared distribution, which is also a continuous, the distribution of a continuous function. If you have, so the way it is constructed, it's a constructed distribution, is that if we have k independent random variables following standard normal distributions, then by definition, if you square these random variables and add them up, you will get a chi-squared distribution with k degrees of freedom. So degrees of freedom are just a way of defining how much information we are using. So you have different distributions, different chi-squared distributions with their associated degrees of freedom. So for instance, the chi-squared distribution with 1 degree of freedom looks like this, the red curve. 2 degrees of freedom, the orange curve. 3 degrees of freedom, the blue curve. Green curve for 5 degrees of freedom, blue, light blue for 10 degrees of freedom. So you can see that it's a continuous distribution, but it is not symmetrical. It's biased to the right, and it tends towards the normal distribution when k tends to infinity. In practice, when the number of degrees of freedom is greater than 30, we consider that the chi-squared distribution tends towards a normal distribution. And when is it used, the chi-squared distribution? It's used to compare frequencies. So we will see examples later. And we can also have a table of the values of a chi-squared distribution. So the difference with the previous table, it's still in the table, the values on the axis, and up here, the alphas are the probabilities. But instead of having lots of different probabilities, we only have a few possible probabilities here. And here we have the degrees of freedom. So for instance, if I'm looking at a chi-squared with 1 degree of freedom, and then I can look at the probability that this distribution is greater than 3.84 is 5%. So we'll see examples when we do statistical testing. Now, the student distribution is a distribution which is constructed using a standard normal distribution, a variable following a standard normal distribution, and y, a variable following a chi-squared distribution with k degrees of freedom. Then if you go z divided by square root of y over k, this new variable, which we call t, follows a student distribution of k degrees of freedom. Now, this is what the student distribution looks like. And the student distribution looks a lot like the normal distribution. It is continuous and it is symmetrical about 0. And it tends towards the standard normal distribution when k, the number of degrees of freedom, tends to infinity. And this is used to compare in the tests of comparison of means. When you've already done a bit of statistics, you know the student t-test, test de student, it follows this student distribution. That's where it comes from. And the same, we can use tables. We'll talk about it later when we do some exercises. And the last distribution that I want to talk about is the Fisher distribution. And this one is constructed with the ratio of 2 variables following chi-squared distributions with k1 and k2 degrees of freedom. And when you look at those ratios, it becomes a Fisher distribution, and Fisher distributions have 2 associated degrees of freedom. And these distributions are also biased to the right, so they are not symmetrical, and they have 2 degrees of freedom, one for the numerator, one for the denominator. And the bias gets less when when the degrees of freedom increase, and Fisher is used in tests of comparisons of variance. So the take-home message is remember the normal distribution, a very important distribution. Remember how to standardize a normal distribution, so to go from any normal distribution to the standard normal distribution by subtracting 0, the mean, and dividing by the standard deviation. And remember that chi-square distributions tend towards a normal distribution when the degrees of freedom are large, and student distributions tend to a normal distribution when the degrees of freedom are large as well. And why is the normal distribution so important? Because it's the main assumption for using parametrical statistical tests. So we'll talk about it again later. So that's the end of the first chapter. And we are now, so do you have any questions on this? It's a basic chapter but then you'll understand better when we go further where some of the probabilities come from, because you've done a bit of distribution. Do you have any questions on that? No? Okay. On Zoom, anyone, any questions? No, thanks. Okay, so next chapter. Chapter 2, we're going to talk about point estimates. Right, so again, this is a very important, it's the start of most of my chapters, because I want you to really remember the difference between the population and the sample. Sample is what is observed, what is known. Population is what is unknown, but that's what we do our assumptions on. So the question is, the question we want to answer is the sample a reliable reflection of what is happening in the population? So how do we know that the sample, what we measure on the sample, is a reliable reflection of what happens here? So one of the things we're going to ask is, how can we give estimations of the real unknown parameters? How do we know that M is a good estimation of mu? How do we know that S squared is a good estimation of sigma squared? So we're going to talk about confidence intervals. How can we estimate either point estimates or confidence intervals? And also extrapolation issues, inference, is what we see in the sample, the relationships we see in the sample, can they be extrapolated to the population? And this is answered by hypothesis testing and statistical tests. So why do we need to rely on estimation? When you want to describe the distribution of a variable in a population, so for instance, if you measure some concentration of a drug in a sample of 15 mice that you've sampled, how would you describe to someone, this is what it looks like, this is what the distribution looks like? Now, one of the things you would probably do is say, the mean is that, and some indication of dispersion, okay? So that's why we use parameters. We use parameters to describe a distribution. And an estimate, what's an estimate? It's an approximation based on a limited number of observations of the true value of the population parameter. So if the sample is representative, then the estimate should be close to the true value. But because it is unknown, we can never be sure whether or not it is close to the true value. And what is the problem? The problem is that we have sampling fluctuations. So if you have a set of mice and you want to conduct experiments on them, if you select 15 mice and do the experiment with them, you'll get a certain set of answers. If you selected 15 other mice, then you would get a slightly different estimate, even if you conducted the experiment in exactly the same way, okay? So that is what we call sampling fluctuations, which means that different samples will give you different estimates of the true value of the parameter. So the question is, how are you going to decide which is the real value? So this is an example. We wish to estimate the real mean weight in a large population P, and we draw a sample of size n at random from a population P, and the mean is estimated using the following formula: theta hat equals sum from I going from 1 to n of the xi over n, where xi is the weight of an individual I in the sample. So that's very easy. I think you would all do that way if you had to estimate a mean. So if you repeat the experiment with k different samples, then hopefully, if it's the same experiment in the same population, you should have estimated means which are close, but they will not be equal. So for instance, the estimated mean in sample 1 might be theta 1 hat. In sample 2, it might be theta 2 hat. In sample k, theta k hat. And so how do you know? So this is the mean weight in kilos. How do you know where the real mean weight in population P is? Okay, you don't know because you can never measure the whole population. So there are two ways of estimating. Either you do point estimates, you obtain a unique value and you hope it's as close as possible, because one of the problems is that you usually can only draw one sample, you only have one study. So you don't know how close or far it is from the real value, the true value. Or you can give confidence intervals. So give an interval estimate. A confidence interval is an interval which has an a priori fixed probability of containing the real value of the parameter. So it takes into account the sampling variations. So, so before we go further into confidence intervals, I just want to remind you, don't confuse the estimate and the estimator. The estimate is the numeric value you calculated from observations in the sample. So for instance, you can say the estimated value of the weight is 72.1, and the estimator is the formula or the mathematical process you use to obtain the estimate. So you can derive the formula such that it's unbiased and convergent. So you can have mathematical properties with the estimator. So if you change the sample, the formula stays the same. For instance, sum of the x divided by n calculate the mean of the sample, but the estimate, the value will vary depending on the observations. Do you understand that? Yes? Okay. If you take a sample and you calculate sum of x over n, you'll get one value. Then you take another sample, you'll get another value, but the formula is the same. Okay. And the formula has certain mathematical properties. So for common parameters, the estimate m of the mean mu is sum of x over n. So that is a formula which you are familiar with. But what is new, because you've known that formula since you were about 10, okay? But now there's something which is new, is that you can actually demonstrate mathematically that if you calculate the mean of a sample drawn from a larger population and you do sum of x over n, that is a good estimate of the real mean in the population, okay? But if you want to estimate the variance, you have to divide by n minus 1. That is something which, if you calculated a variance just of a closed number of values, you would put divided by n. But because you are using it as an estimator of the real variance, you have to divide by n minus 1. And that is what we call degrees of freedom, because here, this m is already an estimate. It's not the real mean in the population, okay? And so that's why we have to subtract another value. So now we come, so this was the point estimates. So either we obtain a unique value with a formula like this, or we use a confidence interval. So because the true value of the population is unknown, the point estimate of the parameter is uncertain because of sampling variability. And so the confidence interval quantifies the uncertainty in the estimation, and controls the uncertainty due to the sampling, okay? So we define a confidence interval with a certain probability. So a 95% confidence interval is an interval that has a 95% a priori probability of containing the true unknown value of the parameter. So we will see, so the rest of the core, in the next few slides, you will see the formula. what you need to know is that the formula to calculate the confidence interval has a 95% probability of containing the real value. So if this is the real value, the dotted line, okay, we don't know the real value, but if that was the real value, then when you calculate the confidence intervals, so that is the point estimate of the mean and then the interval around it, then these intervals will contain the true value of the parameter in 95% of the samples. But there are 5, if you did 100 samples, 5 samples would not contain the true value of the parameter, okay? So out of 100 samples, if you use the formula of the confidence interval, 95 of them would contain the true value, but 5 of them would not. So that's why it has a probability of 95% of containing the true value. Do you understand that or not? Okay. So you have to be careful because we will see in the next few slides. See, towards the end, I will say, so this is how you calculate the confidence interval of a mean. This is how you calculate, etc. These formula, they have a 95% probability of containing the true value, but then when you calculate the value, it may or may not contain the true sample. Right, so now we're going to do a little exercise, which uses what we saw just before. So in a population with 30% of non-smokers, a random sample of 100 individuals is drawn. What is the probability that the number of non-smokers is greater than 40 or between 35 and 40? So you can see this looks like what we did in the previous chapter, okay? But I need to help you first a little bit because we did not talk about the binomial distribution. So what you need to know is that the number of non-smokers X follows a binomial distribution with a probability of 30% of being a non-smoker. And so I haven't taught you this, so you'll just have to say, okay, it's true. We can use an approximation by the normal distribution, which means that X, so the number of non-smokers, follows a normal distribution with mean 30 and variance NP times 1 minus NP. So can you write this down? We'll write this down on the board next to over here. Because we're going to, then you can use it for the rest of the exercise. So X is the number of non-smokers follows a normal distribution with mean equal to 30 and variance equal to 30 times 0.7, so is that 21? 30 times 0.7. Done? Okay. So that's what we know. So you know how to go to Z, okay? And then what is the probability that the number of non-smokers is greater than 40? So you can see I started doing it there. I'm not in N. So if we look at the table, so you can write down just the first bit that's already been calculated for you. P of X greater than 40 is equal to P of Z greater than 40 minus NP, so minus 30, divided by square root of 21, okay? Would you calculate this and see if you find 2.18, see if I haven't got it wrong? Sometimes I get things wrong. So is that 2.18? Did you find that? Yeah, good, thank you. So if we go back to the to this 2.18 is close to 2.17, so that's 0.015, okay? So the probability that x is greater than 40 is 0.015, okay? Now, can you find the probability that x is between 35 and 40? The probability that the number of non-smokers is between 35 and 40. So, you can use the way we did it for the other exercises. So, yeah, if you need to remember what the Z is equal to x minus 30 divided by root 21. So you can find that, and I can give you the table so that you can have a look for the right value. So what did you find? Did you find that? Yeah? Have you not found it yet? Oh, did you find the right value? So the value is 0.125. The probability that the number of non-smokers between 35 and 40 is 0.125. Okay? Now, this is the new bit which involves something a bit different, so please listen. Now I want you to find the interval. This question. Find an interval which contains the observed number of non-smokers in 95% of samples. Find an interval which contains the observed number of non-smokers, so that's X, in 95% of samples. So what we want is find the interval. Look, we want to find the interval which contains, so what is A and B, so that the probability that the non-smokers is in that interval is 95%. So it's the opposite of what we normally do. There we know this and we're trying to find that. And here we're saying if we want it to be 95%, what is A and B? Now I'm going to help you. If you have this distribution, we're saying, so this is the distribution of X, okay? We're saying we want to know where is the interval so that the interval is equal to 95%. So look, please look at the board. It could be over here or it could be over here, yeah? But I'm going to tell you to find a symmetrical interval. So you can say, since in the middle is the mean, you can say it's mu plus C and mu minus C, so that this is equal, okay? So instead of putting A and B, you can write mu plus C, sorry, mu minus C here. Mu plus C. So what you need to do, see if you can find the C. Can you find C? That's what you need to work on a little bit. See if you can find C. Now, if you think carefully, if you listen to what we said before, we have said where 95% of the values were in a normal distribution, didn't we? So there's different ways of doing this.
C'est quoi ça? Là, j'ai donné le Z égale le principe de descendance.
So are you getting there? Would you like some help? Are you getting there? You haven't understood what I was asking, okay. So, do you understand the question or not? No. Yes or no? Yes. Yes, so up till now, we were saying, if X is between that and that, what is the probability? Now we're saying we want 95%. So what are the values that we need here to have a 95% area under the curve, okay? Now, there's one kind of very easy way, which is that. Did I not say in the previous lecture, for any normal distribution, percent of the values are between and didn't I say that? Do you remember when I said that? Do you remember what it was? 95% of the values for any normal distribution are between -2 standard deviations and +2 standard deviations, okay? So, that means that this mu minus C is equal to -2 standard deviations. That would be one way of doing it, okay? So that means that if mu minus C equals -2 sigma, that means that C is equal to -2 2 standard minus C is equal to that plus mu. So minus C is equal to mu minus 2 standard deviations. And if you do it here, that means that mu plus C is equal to 2 standard deviations, which means that C is equal to 2 standard deviations plus mu. So you can write it like this. So that means that here, you could say that X is between, so here we said mu minus C, mu plus C. So that would be 2 standard deviations, -2 standard deviations and 2 standard deviations. So what is sigma equal to? That's -2 times square root of 21 and 2 times square root of 21. So can someone calculate that? What does that equal to?
7,53. C'est 15,06. 2 fois 7,53, c'est 15,06.
Ici? Là? Alors, attendez. Effectivement, so that was one way of looking at it.
Excusez-moi,
Oui,
je me suis trompée. En fait, c'est
alors, pardon?
9,16.
Moyenne,
Moyenne moins 2 sigma. C'est bon ça. Donc c'est la moyenne moins 2 sigma. Et ici, c'est la moyenne plus 2 sigma. Voilà. Mais, donc ça fait 30, oui, 30 moins 2 fois racine de 21. Merci. Et 30 plus 2 racines de 21. Donc là, ça fait combien? Vous calculez 21 et 39, non? C'est ça? Voilà. So, the probability that X is between 21 and 39 is 95%. So that means that we found an interval that contains 95% of the population. Now that's one way to do it, but because you remembered what I said there. But we could have done it a bit more traditionally if that was a bit. So okay, so the way I wrote it here, I wrote it out so that you instead of if you look at this, this is another reasoning, it comes to the same result. Here we say, okay, X is between mu minus C, mu plus C, which means that Z is between mu minus C minus mu divided by sigma. So you get left with this. Is that okay? Between that line and that line. Is because Z is mu minus C minus mu over sigma, okay? Mu plus C minus mu over sigma, because you remember that is how every time we go from X to Z. And so that mu minus mu cancels out, so that minus C over sigma. And this mu minus mu cancels out, so that's plus C over sigma. So that's how we get to there. And then here, this means that Z is between minus C over sigma plus C over sigma. So we just need to find the value such that Z is greater than C over sigma, but we don't know C. But we do know sigma. So if you look in the table for P of Z greater than something equals 0, 0, 25, if you look here, 0, 0, 25 is 196, okay? So this means that C over sigma is equal to 196, or 2, nearly 2, like when we wrote 2. So C equals twice the sigma, so that's the same as twice root 21, and that's how you get the 9. So it's the same reasoning as what we found last time, but with the slightly same result as what we got last time with a slightly different reason. So this was just to show you that you have constructed a 95% confidence interval, because in 95% of the samples, the number of non-smokers is between 21 and 39. So that is a confidence interval. So now we're just going to go through the formula for a 95% confidence interval. And then we will finish the lecture. So maybe what I'll do, or maybe we'll go through I'll just show you, we won't go to the whole lecture. I'll just show you this last one and we'll talk about it next time. So for each type of parameter, such as the mean, or the variance, or percentages, we have different formula. We have different formula for the parameters depending on whether we can consider that the samples are large or small. And then we can have the formula for the confidence interval. So I'll let you go now, but next time we'll do the rest of this lecture and we'll give examples of confidence intervals. Thank you very much. Oui, c'est parce qu'en fait, là, je me suis dit, non, en fait, c'est parce que là, effectivement, au lieu d'écrire moins de C, c'est pas mu moins C, mu plus C que j'aurais dû écrire, c'est juste C. Excusez-moi. Donc, attendez, je me suis trompée. Donc, ici, c'est. Alors, j'aurais pu. En fait, C, c'est juste une variable que je donne. Mais ici, je peux écrire, du coup, c'est moins C et plus C. Comme ça, la distance est C. C'est pour ça que ça me va, en fait. C'est bon? Désolée, je vous ai envoyé. Et là, je fais là. Voilà, alors absolument. Là, c'est juste parce que si Z est compris entre moins C sur sigma et C sur sigma, ça veut dire que la valeur absolue de C, ça veut dire que juste, en fait, ici, ça, c'est pareil que ça.
En fait, tu auras moins Z et plus Z.
Et après, quand vous êtes ici, là, quand vous faites ça, c'est moins C sur sigma.
Ah oui, c'est l'autre côté.
C sur sigma. Et donc, la probabilité que Z soit là, c'est 1 moins la probabilité que Z. C'est 2 là, moins 2 fois ce que j'écris là. Probabilité que Z. Non, après là, c'est pas équivalent, hein, ce que j'ai écrit. Ben, si, ça veut dire que la probabilité. Ce qu'on cherche, c'est le C, donc on veut savoir ce que c'est le C. Donc, juste ce que je dis, c'est que si Z, la probabilité de Z soit entre ça et ça,
Oui.
ces mêmes valeurs, c'est pas la même probabilité, mais on peut en déduire. Ce serait plutôt que dans un sens, que ça veut dire que la probabilité que Z soit supérieure à C sur sigma est égale à. Là, on cherche cette probabilité. Si ça, c'est 95%.
Ah oui, après
ça c'est 2,5 et ça c'est 2,5.
Ok.
Mais c'est vrai que j'ai pas écrit cette partie-là de raison. Bon, je suis partie sur l'autre, d'habitude je pars sur celui-là. Je me suis dit que peut-être ça c'était plus bien, mais je pense que j'aurais dû le revoir la prochaine fois. C'est bon? Ouais. Ça va? Ça va.
J'ai commencé le diapo.
Ah ok, très bien.
Il va falloir tenir compte que j'ai que 10 minutes.
Oui, oui.
Je vais commencer maintenant.
Oui. Oui. Vous préférez l'avoir en français. Et ce que je ferai, c'est que je mettrai en ligne les diapos aussi en français. Pas de problème. Je regarde. Ouais. Après, je pense que
Ça, c'est le je vais présenter ici à la fin, parce que toute la partie d'avant, je pense que c'en est de faire pour la présentation.
Ah, ok, oui. Mais c'est pas grave, il faut que vous fassiez, enfin, quand tu feras la présentation, il y a après, il va y avoir une réunion où on va parler avec Mathieu Alonso, et elle t'a dit si vous allez aller voir et tout ça, c'est bien, elle t'a dit vous allez voir un candidat.
Oui, mais il ne sera pas encore donné la
Je crois que ce sera le 24 mars.
Ouais. De toute façon, elle a dit qu'elle va.
Ah non, non, c'est pas le 24 mars. Demain, en fait, là, il va juste vous allez expliquer. Alors, peut-être que vous allez déjà expliquer ce que vous avez fait et tout ça, d'accord? Même si dans le labo, il y a des choses que nous, on sait, les étudiants, on leur dit de présenter exactement comme ils vont présenter le jour J.
Ah, d'accord.
Tu n'as pas besoin de faire deux présentations différentes. Par contre, quand on fait la réunion le 24 mars avec Mathieu Alonso, tu vois?
Oui.
Au revoir, merci. Là, tu n'es pas obligé de... Enfin, là, c'est pas la peine de faire tout le blabla avant. C'est plus vraiment présenter tes résultats. D'accord?
D'accord.
Mais quand tu le feras au labo, on te fera venir pour une réunion, là. Là, on fait toujours tout comme d'habitude parce que ça te fait un entraînement.
D'accord.
Mais c'est pas grave s'il y a des choses qu'on sait déjà. Tu vois ce que je veux dire?
D'accord.
Alors, par contre, quand tu fais des diapos, il faut jamais écrire du texte comme ça.
Ah, ouais.
Il faut toujours que tu fasses juste les idées clés. Donc, toi, tu vas dire l'acide diéthylénine ou le DTPA est un chélateur qui se lie au 99 technetium. Mais ce que tu vas écrire sur la diapo, c'est par exemple acide DTA, flèche, chélateur, 99 M technetium. Voilà.
D'accord.
Tu vois ce que je veux dire? Il faut vraiment. Alors, bon, mes diapos, elles ne sont pas toujours.